The use of a multi-protocol physical medium attachment (PMA) in communication systems becomes more and more popular. Therefore, let's look at it deeply. First of all, the physical medium attachment (PMA) is a sublayer in the IEEE 802.3 networking model that connects the physical medium dependent PMD interface to the physical coding sublayer PCS. For example, in the PCIe and DisplayPro, this layer is called the electrical subblock of the physical layer. Some other protocols call this block the physical layer. As second questions, we use the term PMA for the IP that addresses this critical function. PMAs consist of a receiver and a transmitter. The PMA includes both TX and RX. The primary functions of the TX include the transmit phase-lock loop (PL) like to a local reference clock, serializing low-speed data from the core to speeds appropriate to the physical medium, driving the signal with a specific amplitude as prescribed by the protocol, performing TX equalization using a finite impulse response FIR filter as a feed-forward equalizer FFE, controlling output impedance to minimize reflection or improve the signal integrity, and performing a detection of a very far-end receiver termination. On the other hand, the functions of the RX also includes the input impedance control to minimize reflections, signal integrity improvement to compensate for high-frequency losses in the physical medium that cause inter-symbol interference (ISI), recovering the clock rate of the incoming data using a clock and data recovery circuit (CDR) for protocols that do not send the clock, correctly sampling the received data with the recovered clock proper phase, deserializing received data into pair streams at a lower speed, and detecting when the physical medium interface transitions from an idle state to an active state. So, the multi-protocol PMA has many advantages as follows. First, it can be configured to address multi-protocol within one physical instance, allowing the SoC to have flexibility depending on the chip programming. The multi-protocol PMA saves die area, package size, and pin count, as well as integration effort, which directly translate to reduced costs. Second, you will reduce the IP licensing cost by allowing different instances of the same multi-protocol PMA to be used for different protocols on the same chip. Third, if some protocols have the same electrical specification, a single multi-protocol PMA can reduce correction time, resulting lower overall project cost and reducing time to market. Fourth, if the goal of the end product is protocol programmability, like field programmable gate area FPGA, the same PMA installation may be used for several protocols. Based on those benefits of a multi-protocol PMA, do you see any practical usage fit your requirements? Yes, there are a few functionalities and usages quite handy for several protocols as follows. First, with a local processor over PCBs backplane, low-loss cabling, or fiber optics as in the PCIe protocol. Second, through a video cable for DisplayPort or HDMI protocols. Then, with peripheral devices using USB protocols. Fourth, between data converters and logic devices with JESD 204B/C protocols. Fifth, between an image sensor and a SoC, as in the SLVS-EC protocol. Sixth, between a DisplayPort and camera and application processor in a mobile device, as in the MIPI D5 and C5 protocols. Lastly, the SoC developers require a multi-protocol PMA that can address more than one protocol. In these cases, they would benefit from having a single silicon Pullman multi-protocol PMA. To support a wide range of protocols, we need to provide flexible options and careful design to every aspect of the PMA architecture. As a result, a versatile multi-protocol PMA design must incorporate many specific features to support all the requirements. Let's look at the requirements of a multi-protocol PMA one by one, and I will show you how Silicon Creation's multi-protocol PMA addresses these requirements. First, the PMA needs to talk to a wide range of data rates, including those are not integer multiples of each other, potentially without access a feed-forward clock. Also, it needs to talk to a clock pattern at next rate frequency, as required in some protocol like DisplayPort. We offer a continuous range of operation from 125 megabit per second up to 16 gigabit per second, over 2 gigabit per second up to 32 gigabit per second, using a proprietary functional TXPO and RX-CDR architecture that supports a wide operation data rate range. As an example, a single PMA can be used to support a 1000 base KX system operating at 1.25 gigabit per second, or a PCIe 4 system operating at 16 gigabit per second. The RX-CDR can lock to a D10.2 pattern as required by the DisplayPort. Second, we must scale the power consumption over the operating range, allowing legacy protocol at lower data rate to keep the advantage of their low power consumption. Therefore, we offer power saving as data rates and TX amplitude decreases. This comes from both intrinsic architecture choice and programmability. Our customers' legacy protocol can leverage low power consumption in their system. Give you an example. One of our multi-protocol PMA with a maximum data rate of 16 gigabit per second delivers a 3x power saving at 5 gigabit per second relative to the 16 gigabit per second. Third, we need to compensate for high frequency losses in the physical medium across a wide range of data rate. Then we provide a programmable CTLE, continuous time linear equalizer, that reduces power consumption as the data rate decreases. The programmability also enables the peaking frequency to shift as the data rate changes. Our most recent PMA offers a 14-tap DFE, decision feedback equalizer. 11 taps are active simultaneously, with 2 groups of 3 contiguous taps that can be enabled respectively between TEP 4 and A and TEP 9 and 14. This multi-protocol PMA also has a TX with a 3-step programmable FIR, final impulse response filter, that can adjust the pre and post cursor from 0.5 to 10 dB in a 0.5 dB steps. Fourth, to meet different swing requirements over protocols, we must have programmable amplitude control over a wide range of TX amplitudes. So our TX has the output amplitude programmability from 100 mV peak-to-peak differential to greater than 875 mV peak-to-peak differential, depending on the maximal data rate supported. This enables support for SAS, where the minimal TX amplitude required is 850 mV peak-to-peak differential, as well as SATA 1, where the maximal TX amplitude is limited to 600 mV peak-to-peak differential. It can also be used for the EDP system, where TX amplitude is required to be in the 200 to 450 mV peak-to-peak differential range. Fifth, to meet the tight interface impedance requirement of many protocols across process variation, we apply a 3-bit trimming input and output termination that can be used by the customer to achieve the tight spread requirement by most protocols. Sixth, the multi-protocol PMA needs to support the DC coupling at the RX interface if the off-chip AC coupling capacitor cannot be used in some systems. Our programmable switch in the RX termination disables the on-chip biasing of the RX front end. Then we apply the DC coupling interface if the front end TX can support the input common mode of requirement for the RX. Seventh, supporting the link figure of merit FOM is required by some protocol like PCIe or DisplayPort, or an ability to look at signal quality at the RX internally. Therefore, our RX eye-opening monitor provides the non-destructive timing and voltage margin for the BIST. Eighth, supporting different bus width depending on the parallel speed that the SoC can support in the core logic is a must. Usually, our multi-protocol PMA provides programmable serialization and digitalization bus width of 8, 10, 16, 20, 32, 40, 64 over 80 bits. Ninth, supporting a wide range of reference clock frequencies and accepting the reference clock from various sources provides flexibility. So our multi-protocol PMA tolerates a reference clock range from 20 MHz to 800 MHz, as well as the ability to accept the reference clock from CMOS, LVDS, or CMOS sources, and can also daisy chain the reference clock between PMA instances. 10th, supporting mechanisms and circuitry for BIST are very helpful. So our multi-protocol PMA has a built-in PRBS, pseudo random bit sequence generator, and checker supporting PRBS 7, 9, 13, 15, 23, and 31. In addition, there are 4 different loopbacks between RX and TX for BIST and debug, including the AC-JTAG IEEE 1149.6 support. 11th, we need to support the exit from idle and LFPS, low-frequency periodic signaling detection, which is required by several protocols to implement power-saving states at the protocol level. So our multi-protocol PMA has a programmable analog signal detector that supports exist from electrical idle in PCIe, SAS, and SATA, and detects LFPS in USB. Lastly, the far-end termination detection is required by PCIe and USB. Our multi-protocol PMA includes a circuit that can distinguish between a valid far-end termination and an invalid high-Z termination. As silicon creations, our multi-protocol PMA development begins with one of the most demanding of all multi-protocol applications, an FPGA. The transceiver in an FPGA needs to work for many protocols. Silicon Creations multi-protocol PMA is used in Microchip's Polar 5 FPGA family of products, which boasts the lowest power FPGA in its class. This is largely attributed to the Silicon Creations low-power multi-protocol PMA that supports, in the Polar 5 device, PCIe Gen 1 and 2, Interlegion, 10G base R, 10G base KR, FCAG, JESD 204B, USX GMI, CPRI 129, SATA, SDI, SGMI 1000 base X, RZ, QSGMI, Sub LVS EEC, DisplayPro, and Cosplace. Following that development, Silicon Creations has developed multi-protocol PMA in various process nodes for many additional customers. As mentioned earlier, the multi-protocol PMA provides an SoC designer targeting multi-protocol in a single RxTX that can reduce the I/O pin count on their chip or reduce IP licensing cost by using multiple instances of the same multi-protocol PMA for different ports. Some examples of customer required protocol combinations are PCIe 4 plus USB 3.x super speed bus plus SATA for memory applications, PCIe 4 plus JESD 204C for a Wi-Fi SoC, V/1 HS plus DisplayPro plus USB 3.x super speed bus in a SoC for display applications, 1000 base KX, 1000 base SX, LX, 100 base FX, SGMI for SoC interface to an optical transceiver and between the MAC and PCS in an Ethernet SoC, and multi-protocol PMA that addresses several serial data transmission protocols with a single programmable design offer significant advantage to the SoC developer. The Silicon Creation multi-protocol PMA is a power and area optimized, high performance, highly programmable PMA that can support a wide range of protocols. It has been successfully deployed in Microchip Polar 5 FPGA, a changing application for a multi-protocol PMA in terms of the number of support protocols, as well as several other customized SoCs. Hopefully, you can understand why you need a multi-protocol PMA based on our 1 decade experience in the multi-protocol PMA development with our lead customers. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.